First of all, my name is Ayşenaz Ergin. I'm from İstanbul Technical University and Department of Computer Engineering. Our approach about protein binding affinity, but we use multiple models and use a consensus algorithm for the results. Purpose of this study, firstly, we want to examine the previous models that have been gained from the previous research and what is the approach, what were the acceptable approach that is studied, and observing the behavior of these models. And we have a hypothesis that models work together more efficiently because every model has a different feature and different perspective of their data. And testing probability theorems algorithmically, like we have mathematical results, and with these results we get outliers, and in our approach outliers are like a little bit confusing for us, so we get rid of them and identify a new method with train of these models. First of all, this was our biggest issue, understand the data. We use MHC molecules. MHC is measure histocomplex, and it's in our immune system and all in animals immune system, but in humans it is HLA. HLA means human leukocytic acid antigen, and when there is a drug or something that you get from your blood system must be attached to this to make it efficient. And this have two classes, HL class 1, HL class 2. First one is class 1 and the second one is class 2. The biggest issue in the first, which data we're gonna use, and because there are different models for different data types. And HLA one a little bit more homogeneous, not perfectly, but more than class 2. And we choose class 1 because their research for binding affinity models are more acceptable, more powerful, and this is our base research for future. And we use HL1, and there are several models, and we can classify them into 3 different categories. First one is score-based, machine learning based, and consensus methods. I'm going to explain it later in details, but these sympathy, I don't know, it is this pronunciation. I look for this a lot, but I just read that, so it can be a mispronunciation for that. Rank path, and this sympathy is the first model that is used in any of these protein binding models, and it is like 1999, and people come with, we can actually use math for this, because in biological way it is more time and more expensive tries for finding protein binding affinity. And then with the future, there are machine learning based methods came into, and NetMHCPan and NetMHC are the most popular ones for that. And consensus methods are like the best results because they use multiple models like us and get the results with maybe some mathematics, maybe some algorithm, but use power of many models. And that MHCCons are like the best results for many research, but I cannot say it is like the acceptable model for that, because every model has their different kind of strengths. And when we use score-based models, the biggest difference between them is the method used to calculate binding scores. They gain a score and label proteins as strong, intermediate, or weak, sometimes strong and weak. And these methods which use more mathematics but not are suitable for all allotypes because they use the similarity matrix, and similarity matrix can be different for all this kind of allotypes, and they assume a homogeneous structure for that. It takes a score matrix algorithm into a center and obtains the binding score with various calculations over it. And the most trending one, like I said, rank fit and sympathy. And sympathy is the first accepted tool to calculate binding affinity. It can use blossom matrix. The blossom matrix has different kinds, and PSSM matrix is one of the matrix that is acceptable for this kind of models. And also this matrix is used for machine learning methods too, but machine learning methods gets a little bit different from that. It is also the limitation of scoring-based approach is their method of calculation predicting stores is relatively simple because they only deal with the linear properties, but the other models can say their biological features like KD values or Codera factors. But this is just for linear properties, and linear properties such as sequence, similarity, and pattern. Machine learning methods are the most trendy in research because machine learning method develops, and this kind of developed for consensus methods too. They have like 4 approaches basically: gathering proven training data, and this was the limitation before because it must be proven training data, and proven data is for biological kind of way. It must get from the biological labs, and IMDb is like the most common database for that, immunoepitope database it is known as. And identifying feature and encoding, and this is like their difference between them. They have different features and different encodings. Like NetMHC gets 50 neural networks and gets the most 10 results from that with Pearson correlation, but NetMHCPan gets a pseudo sequence for the ones that are not in the training data, and gets 50 neural networks like this, and approaches with all of them. And then selecting the model is the one of theirs. Like best model about that, like I said, they have different kind of approaches for that to optimizing and model training and get the results. And they have a machine learning method also. They can presume a value, like mathematical value in KD values in a micromolecule level, and we want that for our approach because we want to them like in a number base and remove the outliers and get the approaches mean value or median value for that. And machine learning based approach identify peptide as a binder or non-binder by producing a score based on a retrieved and represented characters using the training model. So models get their power from their data as this. All the different methods or algorithms are followed. Machine learning approaches like these 4 steps are the baseline for that. Sorry for that. Consensus models, like this diagram is just for representing it. It's like mostly used because they mostly consensus models use 1 or 2 ML and one score based for linear features and the other features for ML features, and they have the biggest reason why there are so many tools, and all of them has different strengths, so they get the results as best as they're possible. But these methods are about combining several methods and making decision on consensus algorithm. There is a consensus there must be. So there must be 2n+1 models, and at least 1 plus n+1 gets the same results for our approach. So one is strong, one is intermediate, and one is weak. That's the biggest problem about consensus methods, that there cannot be consensus about that. And consensus algorithm in this way not only agree with majority of vote, but also accept someone who benefits them all. So it's always a win for the network. The way that this principle of thought that has gained a lot of ground in parallel competition also suggests that our hypothesis that consensus methods can increase their performance because it is all different threads, and we can like multi-threading them and get better performance in a computational way. And first we have our proven data and get the results from different models. And when we see the scores ads, we want like binding affinity and micromolar sites. So ssmpmbec or RankPep is not for us actually, because RankPep is linear coding, and it is in this we have HL A and LMGTLGIVCPI peptides, and it must have a strong binding because we have a threshold for that 0.3, and we assume that lower than this is strong binding. And so we examine all of them, and NetMHC, NetMHCPan, and MHCflurry is acceptable for us at this point. And also we look for another one, and we look for just 138 of molecules. When we see NetMHC and NetMHCPan is acceptable for us. Also NetMHCCons, but NetMHCCons is not acceptable for this point because this is like, I want to show that NetMHCCons is a consensus method, but not always good for binding affinity because because it can be wrong. It has 3 different models in there: NetMHC, NetMHCPan, and pickpocket. And pickpocket is a score-based model, and score-based models can be wrong for that. But NetMHC and NetMHCPan is suitable for us. And this we have our data 187 LA, and there are HIV and HLA binding. And this is the blue lines are for true data, and the other ones is just predicting data. When we see that MHCflurry gets really good results when it's in their training data, but really bad results and gets further from when this is not suitable peptide for them. And also the other ones are like when we get the model's results are can be, how can I say that, can be good for our data to fit in. So in our approach, we get results from every model or compute the given quantity of font results along the specific address. We have 3 different axes, and remove outliers and calculate mean of that. And for another approach, compute mean of font result, but not move the outliers. When we use our approach, we can see that like not this MHC outliers are removed, And these are like the same data when we get closer to our true data. It can be like 100% right, because it's like micromolecules kind of way, and we want just get the threshold a little bit true for our approach. And we kind of examine that what is like in 8-mer long peptides, 9-mer long peptides. When we use HLL1, it's like 8 and 11 mer peptides long. When you use 12 to 20, it is class 2, and we just use class 1 models. So when we examine our data, HLLB is not good work for this approach, but HLA is more acceptable. And also when we go to prediction result, like get the collateral a little bit tighter, we can see that is some of the data is removed, but approaching the true data is a little bit closer. But when we get the quartile a little bit tighter, it's not the best result for us. So best result for us was in the 0.2 to 0.8 quartile range. And then we use median to what is the median fix for our approach. Median is like I can say no big difference about the prediction results as when we use quartile 0.2 and 0.8, but 0.2 and 0.8 a little bit more powerful for us. Sorry for that, I can see. And for future work, we examined that the models are like, okay, it's which model we use is really necessary for our data to know the data and to use that model. But similarity matrices is all over the work, and when we calculate mean square error, there's no big difference between them. But similarity matrices are really concerning for that. And for future work, we're planning to do machine learning methods for creating their own similarity matrices, because when we get to the base level of that, it's all mathematics for calculations, and the mathematics gets from their similarity matrix. In machine learning methods too, because NetMHC, NetMHCPan, they're all using a similarity matrix regardless to their data. So for future work, we're planning to obtain similarity matrices for our machine learning methods. Thank you for listening.